So we want to get into second order differential equations. And this will take a while. This will take a few weeks. But first we want to motivate it with some examples. So one easy example is with physics, with motion. So if you have displacement and velocity is the derivative of displacement and acceleration is the double derivative of displacement. If you have some scenario where you have an equation with all three of those, that is going to be a second order differential equation. To see something more concrete, here's one with a spring mass system. So here we have a spring attached to a wall and also attached to a mass. We'll say the mass is m, usually in kilograms. And the mass is resting on a surface. There's not actually supposed to be space there. And the surface is frictionless, so we don't have to worry about that. And then we pull or push the mass in some direction. Let's just say we pull it. So now it's here. And the amount that we pulled it is some distance u. Then u is the displacement. And then we have the force by something known as Hooke's law, if you've taken physics, says the force from the spring is proportional to the displacement. So displacement times a constant. And then also from Newton's second law, F equals ma, which we've talked about, the force is also m times the acceleration, which is the second derivative of the displacement. And let's just look at the sign for a minute. Let's think about this. If we pull the mass this way, then the spring is going to be stretched, so it's going to pull back this way. So the force should be in the opposite direction. Displacement, it was this way, force is this way. Same thing, if you push it, displacement is this way, force is the other way. So there is a minus sign somewhere here. Let's just write it in Newton's notation to make this easier. So u double prime, and then if we add ku to both sides, we can get plus ku equals 0. And this is a second order linear homogeneous differential equation. Let's just remind ourselves of what all those things are. Second order because we have a u double prime. This one doesn't actually have a u prime, but that's okay. It's still second order. It's like the degree of a polynomial. It's the maximum exponent. We don't have to have all the exponents in between. Linear, meaning it's linear in the dependent variable, so linear in u. And this one's actually even easier. The coefficients are constants. There's no t here. So that's good. And we're actually going to start by talking about second order linear differential equations with constant coefficients. And then homogeneous, remember, this was when you had all of the u's and u primes and all the derivatives of u on one side, and that equaled 0. And what was cool about that? Well, there were a few things, but one thing that was cool was that u equals 0 was a solution. Like the actual function u of t equals 0. Check that out, plug it in, double derivative of 0 is 0, plus k times 0. So certainly the left side is 0. And actually we can see that in this system, because what is u equals 0? That's just the mass not moving, so the spring is not stretched or compressed, so nothing's happening. So of course that's a solution in this case.